Seems like we had an internet dropout. Still not live, are we? Oh, now we are. Guess we back to where we ended before. Scroller. Always get the same notes playing, which is not great. App notes. Always the same. Even after automatically varying a min and max power. Use some help with this one. Remain the same after normalization. Measures suggest that the issue might not be with the normalization process, but rather with the how EEG data is being interpreted or mapped to musical notes. Review the EEG variability. Yes, it does vary quite a bit. So Control F5. And varying the volume. Should we vary the volume with amplitude? Yeah, that kind of makes sense. So there is enough variability.
Look closely at the map EEG data to notes function. Ensure that it's designed to translate variations in EEG data into different notes.
Check the function.
If this function is too simplistic or if the thresholds for mapping to different notes are not set appropriately, it might not be sensitive enough to the nuances in the data.
And let's explain it with GitHub Copilot. GPT-4 to do the same. The function is responsible for converting EEG. EEG data function begins by normalizing power. Function maps each normalized power to musical note using map power note. The mapping is done within a specific range of notes for each type of brainwave. For example, delta waves are mapped to notes between C3 and E3. Yes, that's normalization is not great enough, is it? Yes, so if we're always getting C3, F3, B3, 4, it's always in the low side of the range. So there's not enough variability.
To examine the logic of your map EEG data to notes function, let's break down its current implementation and consider potential adjustments for better responsiveness to the EEG data. Normalize EEG data. It normalizes the EEG data for each frequency band, delta, theta, alpha, beta, using the normalized power function. Map normalized values to notes. It then maps these normalized values to a predefined range of notes.
Yes, it does.
Normalized power to note mapping. How does the function decide which note to assign for a given normalized value? This mapping is crucial. If the mapping is not sensitive enough to the changes in normalized values, it might always yield the same notes. Range of notes. The current mapping uses a limited range, C3 to E3 feet for delta, F3 to A3 feet for theta, and so on. If the normalized values don't vary much or if the range is too narrow, this could lead to consistently mapping to the same notes. Distribution of normalized values. Check how the normalized values are distributed. If most values are clustered around certain points, e.g., always close to 0 or 1, this could lead to similar notes being chosen each time.
Okay, let's do those one by one.
Enhance sensitivity. Adjust the mapping logic to be more sensitive to the changes in normalized values. This might involve using a more granular set of notes or a different method for mapping values to notes.
Yes, on LinkedIn there was a suggestion to use like a table, a lookup table. I assume. So we could try that. Let's check the note again. Yeah, so the suggestion was to have certain EEG markers trigger wavetables. Try it as a prompt in a second. Let's just go with what it already gave us.
Widen the note range. Consider using a broader range of notes for each EEG frequency band to capture more variability. Nonlinear mapping. If the relationship between EEG data and musical notes is not linear, explore nonlinear mapping techniques. For instance, certain ranges of EEG data could map to different octaves or scales.
But we're already doing this. I thought we were already doing a logarithmic. Find the log. No, not that type of log. Should be math log. It should be a scale. It's not cool. I'm pretty sure we had something. So we're not looking at the Python script at the moment. We're trying to do as much as possible in JavaScript. Pretty sure we had the yeah, I thought we already have a nonlinear mapping, but
Nonlinear mapping. If the relationship between EEG data and musical notes is not linear, explore nonlinear mapping techniques. For instance, certain ranges of EEG data could map to different octaves or scales.
Have the normalized powers. Yeah, we're already doing that. I don't know what you're talking about.
Statistical features. Instead of using raw or normalized power values directly, consider mapping based on statistical features of the EEG data, like variance, peaks, or average power over a period.
Map power to note. Hit this bit. Yes, to generate this function.
The map power to note function should take a normalized power value and map it to a musical note within a specified range. The function needs to determine which note corresponds to the given power level based on the range you provide. Here's a basic implementation of such a function. Musical scale definition. The notes array defines one octave of a chromatic scale. Note index calculation. The getNoteIndex function calculates a global index for a given note by considering its octave. This makes it easier to work with a continuous range of notes across octaves. Mapping normalized power. The function maps the normalized power, a value between 0 and 1, to an index between the start and end notes indices. Calculating note and octave. It then determines the corresponding note and octave from the calculated index. Returning the note. Finally, the function returns the note name combined with its octave. This function can be used to map a power value, after normalization, for a note. For example, if the normalized power value is 0.5, and the range is from C3 to C4, it will return a note halfway in this range. Make sure to adjust the note range and the scale as per your requirements.
So this one would not be using getNoteRange. It's using getNoteIndex. Every time you ask it something, it adding another function.
Note index calculation. The getNoteIndex function calculates a global index for a given note by considering its octave. This makes it easier to work with a continuous range of notes across octaves.
Do we have to have another function? Can we just modify the existing ones? Sparsing integer. Already have it in get node range. To change the code to enhance sensitivity. Something went wrong.
Enhancing the sensitivity of your map EEG data to notes function involves making the note selection more responsive to the subtle changes in the EEG data. This can be achieved by refining the way you process the EEG data and map it to musical notes. Here are some strategies to consider. Adjust normalization parameters. Fine-tune the min power and max power values in your normalized power function to better reflect the range of your EEG data. This ensures that the normalization process captures more subtle variations. Use statistical measures. Instead of normalizing raw power values, consider using statistical measures like variance, standard deviation, or mean of the power values over a window of time. Broader node range. Use a wider range of notes for each EEG frequency band. This allows for more nuanced mapping of EEG data to notes. Dynamic node selection. Instead of mapping EEG bands to fixed node ranges, dynamically select the node range based on the characteristics of the EEG data, e.g., higher variance in the data could lead to a broader range of notes. Broader node range. Use a wider range of notes for each EEG frequency band. This allows for more nuanced mapping of EEG data to notes. Instead of mapping EEG bands to fixed node ranges, dynamically select the node range based on the characteristics of the EEG data, e.g., higher variance in the data could lead to a broader range of notes. Use nonlinear functions or lookup tables that can translate EEG data variations into a wider variety of notes. This might involve more complex algorithms that can better capture the essence of the EEG data. Utilize multiple features of the EEG data, like amplitude, frequency content, and temporal changes, to influence different musical elements, such as pitch, volume, and rhythm. Add console.log statements to monitor how changes in EEG data influence the normalized values and the resulting notes. This will help you understand whether the adjustments are effectively enhancing sensitivity. In this example, the node ranges are expanded, and nodes are selected based on the position in the range determined by the normalized power. This approach offers more sensitivity to the EEG data's subtleties.
Let's try this one and get the GitHub Copilot working as well. It's not generating anything. Okay, now it is. Is this legit? Let's comment the previous function out. So we're expanding the range of the nodes. Alpha, beta. Need to log map nodes. Okay, we'll do a log there. Read this and try it
In this
out.
example, the node ranges are expanded, and nodes are selected based on the position in the range determined by the normalized power. This approach offers more sensitivity to the EEG data's subtleties. Remember, enhancing sensitivity might require several iterations of testing and adjusting. The key is to find the right balance that accurately reflects the variability in your EEG data through musical expression.
Yeah, this is pretty annoying. It's always the same notes still. C3, C4. Yeah, just doing the first notes. Let's try channel 7. There's some sort of perceived volume change, but that's actually not changing. Still getting the same notes. So we tried increasing the range.
Normalization not reflecting variability. If the EEG data's variability is not captured in the normalization process, the normalized values might cluster around the same point, leading to similar node mappings.
actually log that variability.
Add console.log statements in your mapping function to log the normalized EEG values and the corresponding node selections. This can help identify where the lack of variation is occurring.
Do we have a console? We do have a no. We had one that we manually saved. How do we do that? I get it properly.
To effectively debug your map EEG data to notes function and understand why it's consistently mapping to the same notes, C3, C4, C5, C6, you can add console.log statements at strategic points. These will help you trace how the EEG data is being processed and mapped to musical notes. Here's how you can modify your function with additional logging. EEG data variability. Check the logged EEG data for mapping to see if the input EEG data varies significantly between different readings. Normalized power values. Observe the normalized powers log. If the normalized values for different EEG bands are very similar each time, it suggests an issue with the normalization process. Note mapping output. The map notes log shows the result of mapping normalized powers to notes. If these notes are always the same, it suggests that either the EEG data lacks variability or the mapping logic isn't sensitive enough to the changes in the EEG data. If EEG data doesn't vary much, the issue might be with the data itself or how it's being pre-processed. If normalized values don't vary, you might need to adjust the normalized power function or the way you're extracting features from the EEG data. If the mapping logic always results in the same notes for different normalized values, consider refining the map power to note function to be more responsive to the input values. By carefully analyzing the output from these logs, you should be able to pinpoint where the issue lies and make the necessary adjustments to ensure a more dynamic and responsive mapping of EEG data to musical notes.
Those work okay. Let's remove those logs for now. Yes, at this too, we expect much normalized powers. Yeah, the normalized powers are super low. 0.06. Yeah, so there's not much variability in the normalized powers. It's scaling from 0 to 1.
The consistent mapping of normalized EEG power values to the same notes, C3, C4, C5, C6, despite their variability indicates that the map power to note function may not be sensitive enough to the changes in the normalized power values. There are a few strategies you can apply to address this. The current note mapping logic seems to produce the same notes for a range of normalized values. Consider revising this logic to be more sensitive to small changes in the normalized values. You could implement a more granular mapping strategy, perhaps using a larger set of notes or a different method to assign notes based on the normalized power values. Ensure that the map power to note function effectively differentiates between different ranges of power values. It might be useful to log the exact values being passed into this function and the resulting node choices to debug effectively. Consider using a nonlinear mapping method if the relationship between power values and musical notes isn't linear. Instead of a direct mapping from power values to note names, you could use a scheme that takes into account more aspects of the EEG data or includes a random element to add variability. For example, you could map different EEG features, like the peak frequency or the presence of certain waveforms, to different musical characteristics, such as rhythm, harmony, or dynamics. Add detailed console.log statements in the map power to note function to understand how the power values are being converted into notes. Log the exact input value and the corresponding output note to see if there's a pattern or if the function isn't responding as expected to different inputs. By making these adjustments, you should be able to achieve a more dynamic mapping that accurately translates the nuances of EEG data into a varied musical output.
Yeah, it seems like obviously the problem is that the change in normalized powers is too small. Current change in normalized powers seem to be too small. How do we address this? Yep.
The issue you're facing, where small changes in normalized powers are not sufficiently influencing the note selection, suggests that the mapping from EEG data to musical notes needs to be more sensitive or varied. Here are a few strategies to address this. Finer note selection. Expand the range of notes used for each EEG band and make the mapping more sensitive to smaller changes in power values. For example, instead of mapping to a range of 4 notes, like C3 to C6, consider using a larger set that includes intermediate notes or semitones. Nonlinear scale. Implement a nonlinear mapping scale where small changes in power can result in more significant changes in note selection. This can be achieved using logarithmic or exponential scales, or even custom functions that better represent the relationship you want between EEG data and notes. Advanced data processing utilize more sophisticated statistical methods or machine learning models that can learn to map EEG data to notes in a way that captures more subtle variations in the data. Dynamic range mapping adjusts the map power to note function to dynamically choose the range of notes based on the spread of the normalized power values. For instance, if the spread is narrow, you could map it to a wider range of notes to enhance sensitivity. Utilize other EEG aspects. Instead of relying solely on power values, consider other aspects of EEG data that might offer more variability and can be mapped to different musical parameters. In this example, I used the square root scale, math, sqrt, power, for mapping, which makes the function more sensitive to smaller changes in power values. By implementing these strategies, you can make the note mapping more responsive to the subtleties in EEG data, leading to a more varied and dynamic musical output.
So this function is currently not being used. Why? Starting to hallucinate because it suggested this change.
In this example, I used the square root scale, math, sqrt, power, for mapping, which makes the function more sensitive to smaller changes in power values.
That also means we have to revert to the previous version of map EEG data to nodes. Something seems to have gone wrong. Generate.
Yes, reverting to the previous version of your map EEG data to notes function could be a good starting point, especially if you plan to implement a new mapping strategy like a nonlinear mapping approach. The idea is to use a function that can be more responsive to the subtle variations in the EEG data. Here's how you can proceed. Go back to the version of map EEG data to notes that work best in the context of your application, or which you feel has the most potential for effective modification. Within the map EEG data to notes function, implement the nonlinear mapping logic. This could involve using a square root, logarithmic, or custom nonlinear scale for mapping EEG power values to notes. Ensure that your map power to note function can handle the nonlinear mapping effectively. This function should be able to translate the scaled power values into a broader and more varied range of notes. After making these changes, it's crucial to test the output with various EEG data samples to see how the mapping responds. Adjust the mapping parameters as needed based on the results. Here's a revised example of map EEG data to notes incorporating a nonlinear mapping approach. In this function, math sqrt is used to apply a nonlinear scaling to the normalized values before they are mapped to notes. This should make the function more sensitive to small changes in EEG data. Remember, the key to a successful mapping strategy is experimentation and adjustment based on testing and feedback. Fine-tuning the parameters and the mapping logic will be essential to achieving the desired responsiveness and variability in your musical output.
So we reverted back, but the range right, this is increasing the range as well, is it? Okay, we're doing the square root already elsewhere. We're doing it already. Can expand the range here though. C3, C6, C3, D6, three, 6. Guess this is HL4. This is no seizure. This is yes seizure. And the notes, yeah, almost the same. So yeah, so the variability between the notes is still too small to our liking. Here it varied quite a bit. Yeah, we have those edge problems as well when you get to the end. Just try quickly. Yeah. That's a lot of noise. Maybe it sounds like music to you, I don't know. Let me know. So So we're doing a nonlinear mapping. I think this range is not large enough. I don't know anything about music, so it's hard for me to tell how large this range is.
The range of notes you've defined in the map power to note function calls is determined by the starting and ending notes for each EEG frequency band, delta, theta, alpha, beta. Let's break down each range. Delta range, C3 to C6, this. This range starts from C in the third octave, C3, and goes up to C in the sixth octave, C6. In terms of piano keys, this covers 3 full octaves, which includes 36 white keys and 25 black keys, totaling 61 keys. The range is from D in the fourth octave, D4, to D in the sixth octave, D6. This range covers 2 full octaves plus 1 note, which includes 24 white keys and 17 black keys, totaling 41 keys. This range starts from E in the third octave, E3, and goes up to E in the sixth octave, E6. It spans 3 full octaves, comprising 36 white keys and 25 black keys, a total of 61 keys. Beta range, F3 to F6. The range is from F in the third octave, F3, to F in the sixth octave, F6. Similar to the delta and alpha ranges, it covers 3 full octaves, which includes 36 white keys and 25 black keys, totaling 61 keys. Each of these ranges is quite extensive, allowing for a significant variation in the notes that can be mapped from the EEG data. The broader the range, the more potential for capturing subtle differences in the EEG data through musical expression. However, it's important to ensure that the mapping logic within map power to note is sensitive enough to utilize the full breadth of these ranges effectively.
Yeah, I'm pretty sure we do not have enough variability in the power, which is odd, considering there is quite a bit of variability there. Yeah, I think I know what the problem might be. The power. Yeah, it should be probably something like 0 to 3000 instead of automated. What does that mean? Why are we doing this again? If I just place this, would it rewrite the function or explain it?
The normalized power function is designed to take an array of power values, presumably from EEG data, and normalize these values to a standard range, typically 0 to 1. This normalization process is crucial for ensuring that the EEG data can be consistently interpreted regardless of its original scale. Here's a typical implementation of such a function. Input validation. The function first checks whether the input is a valid array and contains elements. Finding min and max values, it calculates the minimum, min power, and maximum, max power, values in the array. Handling uniform data. If all values in the array are the same, min power equals max power, the function returns an array where all elements are set to a default normalized value, e.g., 0.5. This avoids division by 0 in the next step. Normalization. Each element in the array is normalized to a range of 0 to 1. This is done by subtracting min power from the value and then dividing by the range, max power, min power. The normalized output is useful for further processing steps, especially when mapping EEG data to other domains like musical notes, as it ensures consistency regardless of the original amplitude of the EEG signals.
Let's try this quickly. This is odd. Very odd. That obviously didn't work. Because it's returning all 0.5s. I was actually generating some noise. I'll return the previous one. I'll just try something more simple. Instead of this two, let's do just 0, because that should be 0. To about 3000. Right, getting a bit more variability there. I want a window size of about 4 or 5. Say channel 7. So this should be seizure. This should be no seizure. The note's actually quite different. So yeah, we're having a problem with that last value there. What does it sound on a different channel? Yeah, that seizure really sounded different. Yeah, so seizure has this lower frequencies. So it was seizure, no seizure, seizure. Yeah, don't know if you're getting much out of it. Does it sound like music to you? Probably highly unlikely. I don't know. It's quite subjective music perception, isn't it? Yeah, that didn't work. Okay, that updated function that you generated did not work. It giving a lot of errors. Now the range now seemed to be better. We're getting a variable nodes when scrolling through the EEG data. Can we make sure we have a nonlinear mapping? Yep.
If you're experiencing errors with the updated normalized power function and want to ensure a nonlinear mapping to enhance variability in note selection, let's approach this step by step. First, let's revisit the normalized power function to ensure it works correctly without errors. We'll keep it simple and linear for now, as the nonlinear part will be in the mapping function. To achieve nonlinear mapping, we can modify the map power to note function. A common nonlinear approach is to use a logarithmic or exponential scale, which can make the mapping more sensitive to changes in lower power values and less sensitive at higher values, or vice versa. Here's an example using a simple exponential mapping. The transform power variable applies a nonlinear transformation to the normalized power. Here, we use a square function, math.pow, power, 2, but you can experiment with other functions like logarithmic, math.log, power plus 1, depending on the desired effect. The transform power value is then used to select a node from the node range. Once you've implemented these changes, test the system with your EEG data. Look for variability in the map notes as you scroll through the data.
Okay.
Adjust the
We get it. We get it. So already you were using. So I wasn't actually listening to what it said. So do it again. Sure that works correctly without errors. Yeah, of course. Why is it suggesting? Is this another function? No, I already have that. It's suggesting changing it back to don't think this will work. Give it a quick go. Let's do channel 5. No, it doesn't work. Someone is asking if using ChatGPT useful or functional. Does it serve any purpose? Yes, it does. Not in this case though, like not in the last prompt for whatever reason is not generating anything useful. Normalized power. Revet. Wait. Let's check that it's working again before we make any changes. Say, which channel do you like? Actually quite different. Did we stuff something up? Yes, we are checking that it is correct or incorrect. I mean, it's highly subjective in this case. So this is how the whole thing sounds. Now the question is what your window size is. Make it very small, say 1 second. Doesn't sound like music. Wait a second, the other thing is we're having issue with this scroller. It's too jumpy. Scroller is too jumpy. Can quickly fix that from HTML scroll min max step. Let's make the step 1. Yeah, let's make it 2. Sorry for that. The other thing is the window size is also step. Sorry. Let's try step of 2. Oh, can you hear this horrible? Like when the notes are transitioning between one another. Yeah, the duration. This duration default should be say 0.5. Play frequency. It's the volume. Make duration 0.1. Oops. What did we stuff up? comma instead of yeah, it's when the transition is not great. Transition is not great. Is it changing at all? No, it doesn't. Okay, let's delete all the input there. Just play the frequency. And same here. And in default, volume should be good. Duration 0.1. Yes, it's trying to, GPT-4 is trying to change the normalized power function. That doesn't work. Nonlinear mapping in map power to node. Yes, we could use, instead of square root, can use a power. So using exponential function. So node index. We need transform power. Should have said that this is missing. Oh, but it doesn't. It's the explanation for it.
The transform power variable applies a nonlinear transformation to the normalized power. Here, we use a square function, math.pow, power 2, but you can experiment with other functions like logarithmic, math.log, power plus 1, depending on the desired effect. The transform power value is then used to select a node from the node range.
It used to work better. As the transition between nodes is really bad. That's something to fix. off. Just keep playing until it's changed. Yeah, maybe that's what we can try next time. Just send a prompt for the duration of the note being played. Can we make it so it continuously plays until the scroller is changed again? So essentially when we load the page, nothing happens. When we start scrolling, the note is played until we move the scroller again. Yep.
To achieve the behavior where a note continuously plays until the scroller is moved again, you need to adjust the logic around how and when sounds are played and stopped in your application. Here's a strategy to implement this. You'll need a global variable to keep track of the currently playing sound, or oscillator, so you can stop it when the scroller is moved again. Modify the play frequency function to check if a sound is already playing. If so, stop it before starting a new sound. In the scroller's event handler, ensure that moving the scroller stops the currently playing sound and then starts playing the new sound corresponding to the new position. Global oscillator. Current oscillator is a global variable that keeps track of the currently playing sound. In play frequency, before starting a new sound, the existing sound is stopped if current oscillator is not null. The file scroller event listener stops the currently playing sound and starts a new one based on the scroller's position. With this setup, when you load the page, no sound will play until you start scrolling. Once you scroll, the sound for the corresponding position will start playing and will continue to play until you scroll again, at which point the sound will change.
Yeah, that sounds good, but why do I have a feeling this code would not work?
It looks like your message might have been cut off. Could you please provide more details or clarify your question so I can assist you better?
Didn't actually say anything. Which stack we are using? What are we using? Flask. It's a Flask application. Hopefully it will soon be available on bionicchaos.com. Still in development, but we, as you can tell, it's doing something kind of useful, which is loading this EEG that has a seizure in it, epileptic seizure. This is pure EEG, like the highest quality you can get. It's from an implant, from 16 implanted channels, implanted electrodes sitting on top of the brain. 8 on the left, 8 on the right. Now we wanna, this tool allows you to do denoising and other things, but there's another feature. We wanted to play sound, which it does, but we haven't published it yet. So when you load the page, by the way, it won't show you the whole spectrum because we're essentially turning power in each frequency band, delta, theta, alpha, beta, into a corresponding musical note. So you select your channel, scroll through the stuff, and then write in the comments if this sounds like music to you, or if you like it or not. If you don't like it, you have to make a suggestion as to how to improve it. You can change your window size and the like. And now, from next time we are working on this tomorrow, we'll be trying to actually make it play continuously until you move the scroller again. So loading the page doesn't play anything. We're actually not allowed. The browser won't let us play anything. And select your channel and just start playing. We want to make it so it keeps playing until you move the scroll again, and then we'll play the new 4 notes. Already have an event, obviously, for the scroller input. Where is it? Over here. Yes, that's the same. And then we're changing the play frequency function. I can get rid of that. This function will still have volume and duration as an input. Why?
Global oscillator. Current oscillator is a global variable that keeps track of the currently playing sound. In play frequency, before starting a new sound, the existing sound is stopped if current oscillator is not null. The file scroller event listener stops the currently playing sound and starts a new one based on the scroller's position. With this setup, when you load the page, no sound will play until you start scrolling. Once you scroll, the sound for the corresponding position will start playing and will continue to play until you scroll again, at which point the sound will change.
Okay, we'll continue this next time. Bye for now.